Michigan, my home state. I went to graduate school there for a year in physics. He received a PhD in 1990 from UC San Diego, and he's been employed at Scripps since 1977 and by the U.S. Geological Survey since 1991. So, Dan, welcome.
So I'm gonna turn on this roving microphone. Are we gonna interfere? Yeah. Okay. Good. Wow, what a great place, and it's a pleasure to participate in our collective learning, because oftentimes we learn as much as you do, or maybe more. You know how that works. The professors have to scramble. So the way this is organized is I'm going to talk about, I'm a climate scientist and a physical scientist. Julie is a person that actually works with decision makers and people that are trying to understand these processes in order to develop policy and actions. So I'll sort of give the more ethereal view, and Julie will tell you what really is important from a decision maker standpoint. So you kind of get both of that, and if this works as to form, I won't take so much time, so that after we're all done, we can talk and answer questions and so forth. So the sea level rise problem is a critical problem for the state of California, and of course there's many different settings. We have hundreds of miles of open coastline and estuaries, in addition to a very large estuary where we're quite vulnerable if sea level rises and so forth. So I want to give you a little flavor of that. I think I have 17 slides, so I'm sort of trying to throttle myself back. We are supported by the state and federal agencies who are both interested in improving the quality of climate information for stakeholders, for decision makers, and would also like to know how decision makers use information. And consequently, with Julie and other colleagues' help, for example, we're polling decision makers in California to understand where they stand on sea level rise, what their sources of knowledge are, what the gaps in knowledge might be, and what their priorities are. So that's an activity that Julie and I are working on together with other colleagues. Jerry mentioned that of course sea level rise is set upon us, and sea level rise, of course, happens naturally. It happens because the Earth has natural variability in its climate system, and an index of the climate system is actually the carbon dioxide concentration in the atmosphere. Carbon dioxide is critical in this discussion because CO2 is a greenhouse gas, meaning that once in the atmosphere, it provides an important part of our energy balance, in that CO2 and other greenhouse gases like methane and the fluorocarbons and so forth are not transparent to the radiation that leaves the Earth's surface. They they actually absorb, and because they absorb, they re-radiate. And if we change the concentration of these greenhouse gases, we are changing the effect of this heat-trapping nature of the atmosphere. Now, the greenhouse gas, the greenhouse effect and greenhouse gases are a good thing. The moon, for example, doesn't have much of an atmosphere, and it has very little greenhouse effect, and it is a very harsh environment if you had to live there. The temperature swings on the moon are just really, really intense. So the greenhouse effect is in its natural form is what we've evolved under. One of the important greenhouse gases, for example, is water vapor. And water vapor is involved in climate warming as well. But the reason that CO2 is so important is that, as you can see with ice ages and so forth, if we go back on timescales of thousands, hundreds of thousands of years, we've had these rather cyclic oscillations, and you could say, well, okay, so we've changed CO2 a little bit. It's changed a lot over Earth's history, and that indeed is true. But you notice that over the last 400,000 years, there's sort of a top of the envelope to the variations in carbon dioxide in the atmosphere. And the top is about 300 parts per million by volume. And recently, now we're up here, we know that that excess of CO2 that has occurred since the beginning of industrialization on the planet is essentially not natural. It is labeled isotopically, and from that labeling we know that it's fossil carbon. It's fossil fuels that have been burned, gas and oil and so forth. And so we are entering an era where we're getting well outside the bounds of what the planet has seen over the last few 100,000 years in carbon dioxide. And you can see the little inset where we think we know what CO2 was 1,000 years ago, because CO2 is trapped in ice bubbles in high latitude settings where ice cores are taken, and we can determine that the concentration pre-industrially was about 280 parts per thousand, when the climate was pretty much similar to what we have today. Right now it's about 390, so the difference is about a third over what it would have been if man hadn't been active. This fellow, his name is David Keeling, one of our former colleagues, unfortunately passed away about 6 years ago, really had a profound influence in making observations of carbon dioxide in Mauna Loa in Hawaii, and noticed after just a few years that in addition to this cyclic nature annually, see, the Earth kind of breathes as plants photosynthesize, and particularly in the northern hemisphere, because there's lots of land masses. So there's this annual cycle. But in addition to that, Dave Keeling noticed that there was this sort of incremental step up, few percent per year, and of course that's continued to rise through the last 5 decades or so. And of course, if he had the luxury of observing earlier than that, he would have seen this rising even before. So that gets us to, I want to assert that the CO2 problem, because it changes the temperature of the Earth's surface is changing sea levels, because it's warming the oceans, and as the ocean waters warm, their density becomes lower, especially near the surface where most of the heat is absorbed, and consequently they're rising because of thermal expansion. But it's also changing sea levels because it's melting the ground-based ice on the planet, and that's running into the oceans. To give you a counter example, when the Earth was cold during the last glaciation, going back 20,000 years or so, sea levels were several tens of meters lower than today, because a lot of the water was bound up in the continental ice sheets. So this is a reckoning of what global sea levels have been going back to the late 1800s. This is the longest record of sea level along the West Coast. It's the station near Golden Gate in San Francisco. And well, the global average of sea level, which is estimated from a bunch of tide gauges and more recently from remote sense observations, is relatively smooth. The San Francisco record is a lot more volatile, but in fact, the San Francisco record is a pretty close mirror to what we've seen globally in sea level. And interestingly, if you look at some of these big peaks and you correspond them with a year, you would find that a lot of those very large years are El Nino years, which of course are big weather and climate makers here in our landscapes.
Yeah, before you leave, can you go back to 6?
Yeah, and by the way, even Jerry is allowed to ask questions, even though we're going to have to charge him more if he asks too many.
Go back to that slide. I want to ask you, why don't you say a word about that statement on the bottom in the new paper that came out from some of your colleagues within the last day or two?
Oh, you want me to say something?
Yes.
I thought you were going to say something. What did you want me to say? I mean, okay, so.
No, but the recent 2 decades haven't seen much.
Oh, yeah, well, okay, so that's getting ahead of us a little bit. I am going to address that, but Jerry knows too much. We are going to talk about this turn of events here along the West Coast, where the global sea level has risen at approximately 3 millimeters a year, and that doesn't seem like very much, but when it accumulates, it's a problem. And our sea levels here along the West Coast seem to have kind of plateaued. They've bounced up and down, but they don't seem to have followed this strong increase. So yeah, let's just leave it there. The other thing I wanted to say about greenhouse gases, which I think is to the point, is that Jerry mentioned wicked problems, and wicked problems are often problems that are ones in which the impacts don't seem so evident at the inception of the problem. And in this case, what we have is we have essentially a small segment of society, scientists that are saying there's a problem, and they're pointing to a 2 or 3 millimeter increase in water levels every year, and everybody looks at that and they say, well, that's hardly perceptible. And look here along the West Coast, it's, looks like it's pretty much the same as it was in 1995. So what's the big deal? But the thing about the greenhouse gas problem is that greenhouse gases have a long lifetime. They have CO2 doesn't wash out of the atmosphere like aerosols and other contaminants. So the residence time of CO2 is more than 100 years. And what that means is that even small changes in our abilities to either continue on a high fossil fuel economy or to mitigate that somehow, even though they're not immediately apparent, it's like compounding interest in your bank account. You know, if I were to say, I'll give you 8% on your investment, and Jerry said, I'll give you 8.5%. Well, right, you know, over the next year, it doesn't really make that much difference unless, you know, you're a billionaire or something. But when we allow that to compound over 100 years, the smart people who took Jerry's offer would have probably done better than my offer. And similarly, if we can limit CO2 and other greenhouse gas emissions somewhat in the next few decades, we're going to be in better shape for the next generation and the next generation. Okay, and in fact, it's about, in many of these climate simulations, you can't really detect the impact of different policies until about 50 years out. And that's another property of a wicked problem, is that we can do all we can to try to fix it now, and we won't see most of us won't be around to see whether it worked or not. So that's kind of wicked, I would say. Okay, so this is what Earth's temperature looked like as we can reckon from proxy records, from records that are collected from tree rings and corals and sediments and the like, not directly measured by thermometers, because 1,000 years ago we didn't have thermometers and people weren't recording temperatures. And what we can see here is that over this 1,000-year interval, think of this as just the long-term average. We'll call that, well, it looks like it's, the average that this is referenced to is the average during the instrumental period, so it's a little bit below that. But you can see that the fluctuations annually and decadally and so forth are something like a degree. These are in Celsius, these are in Fahrenheit, but not too much. When you average the whole globe together, this is the global average surface temperature estimate. And you know, it's not perfect, but it's probably a fairly good characterization. You can also see that as we got closer in time, we got more observations, so we've narrowed the uncertainty, so to speak, but there's still natural variability. We know that. We know that one year differs from another and so forth. Now, if we superimpose the instrumental record where we did have thermometers at the Earth's surface, along with this, we can see that over the last 150 years or so, temperatures have continued to vary, but they've gone up a bit. And unfortunately, my graphic, actually where we are right now is about here. Actually, see right here, that's the red curve. And you can see that particularly during the last 3 decades, temperatures are starting to push outside of that envelope of variability. And now here, these are the temperatures that are projected by climate models. Climate models are numerical models. They're just computer simulations that represent the Earth's atmosphere, oceans, land masses, and ice, and so forth. And they're the laboratories that we use to look ahead, because we think we know the physics and thermodynamics and the various processes that are involved in creating climate and climate variability in the past. And of course, if we have them accurately depicted in these models, then we can run them forward and look what will happen in 100 years at the end of the the present century. So you can see that the projected temperatures at best are something like 3 degrees Fahrenheit above today's levels. That's 0 here. This is, by the way, is the annual average Earth's surface temperature. 3 degrees Fahrenheit doesn't sound like very much if we're talking about day-to-day fluctuations in Long Beach, but when we think about it, if it's day-to-day and we average it over many years and many locations, that's a very large increase. And the largeness we can kind of scale by how large it is relative to this variability. 3 degrees is the lower end of this envelope. The upper end is well up here, 8 or more degrees Fahrenheit above normal. That's enormous. That's the difference between Long Beach and Palm Springs or something like that, okay? And we could really feel that even on a day-to-day level. Now, the reason, there's a lot of uncertainty here. There's different climate models. We don't like to rely on one model, just like if you're a stock market investor, you don't rely on just one prognosticator. You probably listen to several and try to understand a consensus, and that's what we do with climate modeling. The other thing that is involved in this envelope is that there are different assumptions about future emissions, the fluxes of CO2 and human decisions and so forth in seeing what, perhaps limiting or perhaps not our carbon-based economy. And so that's wrapped up there too. The higher the emissions, the higher in this envelope that our pathway will take, and the lower, hopefully the more moderate will be the temperature increase. But what you can see is that even under the best circumstances, according to this swarm of climate simulations, we are going to be confronted with a climate that is very different than what we have grown used to and essentially what civilization has developed under. So back to sea level. This is the record at San Francisco, the actual record of sea level back, in this case, to 1900. And we can see that along this coast in California, we think that sea level has risen approximately 7 inches over the last century, about this much. And in fact, that 7 inches is very similar to what we would see from the global average of sea level rise. That's about 2 millimeters a year. I used that number previously, and I'm sorry, I'm mixing metric and English, but we all sort of talk in the metric units. This is projections of, I don't know what I just did, but I didn't mean to do it. Okay. This is projections of sea level in the past, and this is what global sea level has done over the last century, and that global rate is, as I mentioned before, is about the same as what's happened in San Francisco. And what we can see is that what we're looking towards, because the Earth is warming, because the oceans are warming up, and there's thermal expansion, which will result in something like, I'm going to say 8 to 10 inches of sea level rise over the next century, just because the oceans are warming up and the oceans are consequently inflating. But the other part, essentially the big major component of sea level rise, is the fact that we're melting the big ice stocks on Greenland and Antarctica, as well as land-based glaciers, but largely the former are contributing. And just to give you an idea, if all of that ice would melt, we would have something in the neighborhood of 70 meters or so of sea level rise if we were to melt all that ice that's contained there. I hope I have that number right. I'll take that as my homework problem, and I'll correct it if I've got, it's at least 70 and it might be 200. Do you remember, Julie?
I don't remember.
Okay, so I'm having a senior moment, but you'll forgive me, most of you. Well, anyway.
If you lower it, if you raise it, no.
Okay. I won't. It's at least 70, but it's more than that. Well, okay. So sea level by itself, if sea level was to rise kind of gently and smoothly, even if it rose, let's go back 1 second. If it rose, this is a meter. That's over 3 feet of sea level rise from present day to 2100. And right now, the upper end of those estimates are pushing between 1.5 meters and 2 meters above present day levels. So that's a lot of sea level rise. The lower end now is something 2 to 2.5 feet by 2100. And again, I could give you the sermon about, high greenhouse gas emissions, lower emissions. We want to be on that lower pathway. But again, it's often, particularly in the early stages of sea level rise, it's not so much because the sea level has risen by itself, it's because that is compounded by big storm events. And this is the record, again, this is at San Francisco, but I didn't have time to dig out the Los Angeles or the La Jolla record of tidal records, where each dot here is a tidal observation, and the blue trace here is the tide prediction that would be the astronomical sea levels. This happens to be in 1983 in the wintertime. This is the period of late January of 1983 when we had a very large El Nino, and we had particularly here on the 26th and 27th, we had very large storms. This is the highest hourly sea level on record for many tide gauges along the West Coast, this 27 January of 83. And the excess sea level above tide prediction was approaching 2 feet because we had very low pressure, so we have what's called an inverse barometer effect on sea level. As atmospheric pressure goes down, sea level goes up. And we had wind-driven storm surge effects on top of that. And we also, it turns out, during this episode, this happened during relatively high tides, these high spring tides. Tides are highest during full moon and new moon. And along the West Coast here, we have the highest tides in summer and nearly as high tides astronomically in the wintertime. Fall and spring, not as high. So the wintertime, of course, is our vulnerable period because we have the opportunity for big extratropical winter storms that sweep across the Pacific Ocean. And El Niños have their own effect where oceanically they transmit a current and warm water along the West Coast, and that elevates sea level on its own. So we have a conspiracy of different factors during wintertime, and particularly during El Niños, that cause sea levels to be exceptionally high. This is a count, again at San Francisco, of the total hours, and I just accept the fact that this is the extreme, and I chose the 1 in 1,000 level of hours and asked the question, how many times in a year did we exceed that amount? And you can see 1983 here was essentially the leader of the pack. This is 1998, which was another very large El Nino, and this shows their cumulative amount above a certain this threshold and so forth. So you get a story where this doesn't happen every year. Of course, it happens episodically a few times in our recent memories, but it's times like this, and I think Julie's going to probably tell you about some of this, where we have the biggest impacts along the coast here. Now, to Jerry's question about the last few decades. Well, so in the early 1990s, the observation of sea level was kind of revolutionized because satellites were launched in which altimeters, devices that can measure distance from a satellite to the Earth's surface very precisely, were flown, and oceanographers learned how to harness those observations and essentially map sea level around the globe. And so they were able to make maps of, in this case, this is the trend, the ups and downs of whether sea level over time during this epoch, starting in the early 90s and proceeding through about 2010 in this picture, whether the ocean was increasing over time in its sea level, or whether it was actually declining or staying about the same. So the color scale here, well, I told you that on average the global sea levels have been increasing by a couple millimeters a year. So we wouldn't expect this picture to be blue, because that would mean, you know, if it was all blue, that would mean the oceans were losing water, they were losing sea level somehow. Maybe we were in an ice age. That's not happening. The map, if you sort of eyeball integrate it, is mostly positive. That means that these trends are in millimeters per year. And I told you that the average was between 2 and 3. So your eye should, you know, if you had to blend all these colors and you mix them, what you'd find is that the color should be yellow-green, okay? Now, there's some blue here and there's some red there and so on and so forth, but the average here, it turns out over this interval, is about 3. But interestingly, as Jerry pointed out, the sea level along the west coast hasn't really changed that much. See, it's in the sort of aqua color here. The big changes across the Pacific Basin have been in the western Pacific, near Australia and Korea and so forth. We think that is a wind-driven effect, and we think that it's natural variability. We think the climate system across the Pacific has these slow fluctuations in climate, and as they do, they maneuver water at the surface from one side of the basin to the other. And this is a picture where the water has obviously been pushed to the west. The implication is, if this is a natural fluctuation, that at some other point in time, when we have another class 20 years from now, and we look at this picture, we might see red over here and green over here. If that's the case, then we're going to have a hastening of sea level rises along this west coast. This again is the global average. So we've played a little game. We've made a little model where we know tides can be predicted for a century because they're very well constrained by tide-producing effects, orbital, sun, moon, planets, and so forth. We have superimposed on that the changes that would be developed, we think, from a changing climate as well as the weather in a climate system. And over time, this is what that sea level would do when you look at all the tides and so forth, and I've just plotted them all. This is hourly over, here's today. We also run climate models retrospectively as well as prospectively, so we can run these backwards. But you can see now how, especially these extremes, really push the envelope over time. And this is the count of the number of hours exceeding a very high threshold. In fact, this is 1 in 10,000. And where today, the average of today's climate is that happens about once a year. And you can see in the future that that's all of a sudden happening many times a year. Now, when sea level, oftentimes when we have these high sea level stands along this coast, and in fact even along the Gulf Coast, it's not happening when the ocean is placid, it's happening when there are storms. So there's waves involved with high sea level stands, and that adds to the impacts that Julie is going to talk about. This is a scene up near Monterey during that winter of 1983 where the oceans were exceptionally high. We had big several meter swells that were coming in, as well as wind waves, and the waves were washing over this real estate and out into the street and then back through, and it was a legendary winter. We had, during that winter, this is San Francisco again, and I showed you a picture of the high sea level stands here. This is in centimeters, so you can see these big events that happened that winter, and you can see that big storms represented by low barometric pressure in a couple of cases coincided with the highest astronomical tides. That's this one. And those storms, in fact, also had very large waves. This is the waves measured offshore. These are measured in centimeters. These wave heights are measured in meters. And so we had a really amazing winter. The other thing that, in just sort of coming to a close and what I wanted to talk about, our water system in California, to a large measure, is drawn through this estuary, the top part of the Sacramento and San Joaquin Delta. A lot of the high-quality fresh water in the state is generated and delivered north of the city of Sacramento, and 70% of the water that's consumed and developed is used south of Sacramento. So we have this quite amazing engineered water system where we have plumbing that comes through the delta and feeds the San Joaquin and the urban communities south of the Grapevine. So this is a key piece of real estate for us, as well as, of course, being a very sensitive set of ecosystems here. And there's levied islands, and there's real estate, and all sorts of infrastructure and so forth that goes through there. So if sea level is to rise, it's going to penetrate into this estuary, and it's a big problem for us in California. That estuary is one where it's not only susceptible to the rises in water levels because of ocean conditions, it's also susceptible to flooding. This is a segment from San Francisco up to the I Street Bridge in Sacramento, and these are water levels that were these are the maximum water levels in a rather short record that I took, and you can see that we are 8 meters, that's 25 feet or so above some datum at I Street. And of course, what we're seeing is the impacts of floods there that would compound what happened in sea level rise. This is just a glance at the Bay Delta in normal circumstances, and now this is a scene from 2006 where we had quite a lot of water in the system from winter storms. So with that, this is not a real happy message. This is one of those issues that Jerry mentioned, that we have a big management problem that is challenging us, and I think Julie is now going to talk about some of the comings and goings of how that's playing out. So, let's see.
Dan, how about questions or comments for Dan before?
Oh, you want to do it that way?
Let's see if anybody has any.
Okay.
We know that there's plume water at the equator because of the force, the way Earth turns, that is higher than sea level. How does this affect that plume of water in relationship if we're rising in the Pacific and it's coming down? How is it going to affect it? Is it going to build higher, or is it going to build lower?
Yeah, what I showed you in terms of those trends were the trends above the average. So all those features that you know about, and maybe not everybody realizes, that across the tropical Pacific, if you were able to measure the average level of the ocean, you would find that actually the Western Pacific stands over a meter above the Eastern Pacific level. And that's because of wind-driven effects. The planet is rotating, there's winds, and it's heated by the sun, and the Earth reacts. So in fact, the sea level rises that are anticipated are probably not going to be uniform everywhere, and they're going to be modulated by these circulation systems to the tune of tens of centimeters, probably, differences between the far North Atlantic and some equatorial places and so forth. I'm not prepared to talk about all that tonight, but know that sea level rise isn't going to happen monolithically across the ocean basins. It's going to differ depending on various factors. The other thing.
Is it also going to move? Is it going to move? In other words, the point is, I'm at sea level today. Tomorrow, am I in trouble? Or when it once adjusts itself?
Yeah. Well, everybody.
Will it keep that adjustment, or will it change?
Well, let's put it this way: that just about everywhere is going to, if the average of the oceans inflates by, let's say, 3 feet, everywhere is probably rising by at least 1.5 feet. But some places might rise by 4 feet, and some places by 2. Okay? Yeah. And where and how is going to be dictated by the winds and by ocean circulations and so forth.
Thank you.
Yeah.
Do you think the continental shelf may have some effect on whether a certain area gets warmed or not? For example, on the Atlantic side, the shelf extends way out to the ocean, and on this side, Pacific coast, our shelf is deep.
Uh-huh. Well, so a lot of the heat that is absorbed is in the first few tens of meters of the ocean, but in fact, some of the heat is now being deposited in the the very deep ocean. But I don't think that shelf width and shallowness and deepness of the margin is a huge influence, because those effects, remember, sea level isn't happening locally, it's happening over the scale of a whole ocean basin. And what's dictating what's happening along a shelf is often dominated by wind-driven effects, okay? Now, that shelf configuration and so forth has an effect on tides, and it may have an effect on big storms and storm surges, so that under extremes that could play out. But in general, I would say the sort of bathymetry that you're talking about is not a real significant issue.
But if there's a fair, if the surface heats and the Atlantic conveyor recycles that, it would still warm down lower than the solar warming would happen.
Oh, yeah.
It would be forced down as part of the ongoing conveyor system.
Yeah, the abyssal areas are going to warm, and now there's actually been temperature changes detected at a few thousand meters of the ocean, but most of the warming is above the permanent thermocline, which is hundreds of meters. Yeah, but over long periods of time, this whole thing could upset this big circulation cell that you mentioned, the so-called conveyor belt, and we're probably getting into foreign territory for some of us, and it might require another lecture. But that, over very long time scales, there could be other effects that are brought in because of the interruption of heat that is exported poleward because of these circulation cells. But in the next 100 years, probably not.
One of your initial slides had peaks at about a periodicity of 100,000 years. Is that what I?
There's several. Yeah, there's several orbital periodicities that are involved in producing the interglacials and glacial cycles. Yeah, and that goes back for several hundred thousands of years under the...
Ice ages have a periodicity of what, 20,000 years? And you haven't said anything about ice age. Is that
Well, let's...
an overlay?
I'm sorry, Julie.
That's all right. I know.
Stand by. Julie's coming. Let's let the data tell us. Okay? You have to recognize that when you talk to me, my expertise is sort of concentrated in this arena right here. But I'll try to take your call and raise it $5. Oops, there we go. Okay, so in this epoch of 400,000 years, 1, 2, 3, 4 ice ages, or these are actually interglacials are the ones that are high CO2. When the Earth's climate cools, the CO2 in the atmosphere drops, and they're linked, because as climate warms, it releases more CO2 because plants in their domain expands and they're photosynthesizing more, and as the whole planet cools, it goes the other way, and as CO2 rises, it adds to the heating that's caused. This is driven by solar forcing in the way the planet is heated, but it's accentuated by the way the atmosphere reacts to that. Okay, so if you were to model the climate changes that we see here, and you did not include the atmosphere, the greenhouse effect, you'd be off, because the greenhouse effect is an amplifier. So it's an essentially a positive feedback as the Earth goes. So it looks like the primary periodicity here is about 100,000 years. Turns out that the last glacial was this period here, and that's the 20,000 years ago one. But we really need a longer record, because there's some very long frequencies in this orbital parameter. So I'm not sure that if we looked at a record that's another 400,000 or so years, we would see this periodicity quite as strongly as we see here today.
Let me make a comment on this.
Oh, Jerry, go ahead.
Because I think it's important to keep in mind, Homo sapiens emerged somewhere in here, 100 to 200,000 years. We had other Cro-Magnon going back million, but Homo sapiens in here. It was only here, 10,000 years ago, that we began to settle into communities, because that's when agriculture started. So all of this time, 90% of it, we were hunters and gatherers, so it didn't really matter very much what happened to sea level. Yeah. And it's most of our big cities and our civilizations have developed during a period of relatively stable sea level.
Yeah.
And so this is what's causing the problem, because we've invested billions of dollars to create cities and all of the infrastructure. And so when people say, well, you have to relocate, you're the mayor of Laguna Beach, you know, as you say, it's a wicked problem. You're not going to go to the city council and say, look, guys, we're going to start to move in one.
Yeah.
You won't even serve out your term limit. So these are all, they're really serious issues. And if you look back over geologic time, interglacials in the past have lasted about 10,000 years, plus or minus a little. This one's already lasted almost 20, and there's no indication that it's going to stop. That this natural signal is going to overpower the human. So,
Certainly not in the short term.
not in the short term. No,
Yeah.
maybe way out here,
Yeah.
but not in the short term. Yeah. Anybody have one more question? Otherwise, I'm going to bring Julie up. Dan, thank you.
Sure.
So, all right, our next speaker is Julie Thomas. Julie has been at Scripps for the last 30 years. She's the program manager of it's CDIP. It's the Coastal Data Information Program. And that's the one that has the buoys offshore, they measure the waves. And when we did
So
an
this is
exhibit
forward and
called
back.
Catch a Wave, which was, I guess, 3 or 4 years ago, Julie was very helpful to us and provided a buoy and certainly helped us with the design of that exhibit. She is also the executive director of SCOOS. SCOOS is the Southern California Coastal Observing System, which is part of IOOS, which is the Integrated Ocean Observing System, which is GIOS. But she promises she's not going to use all of these acronyms, and she takes all of this stuff that Dan and his colleagues have created and makes it make sense to the policymakers, to the decision makers, and she is working with certainly people all up and down the coast, and particularly I think around San Diego. But she's going to tell us how then you translate some of this into policy issues. Thank
Great.
you very much.
Thank you, Jerry, and thank you very much, Dan, for setting that overview of our sea level rise wickedness here. So, yeah, there's lots of instances in our state that look like this, and the question is, how are they going to be handled? What are these homes, are these locations? What are they going to do as sea level rise becomes more evident in our communities? And this way. All right, so are we taking it seriously? We've seen these cartoons in our newspapers for quite a few years now, but all of a sudden people are thinking, well, maybe that's not so funny as more and more data comes online and more evidence of our problems of sea level rise and climate change. So what I really wanted to do tonight was just address a couple of the state, federal agencies that are taking some action, and kind of bring that down to our local community area to try to see what we can do going forward. And you know, some of the planners are looking at it seriously. Some are just doing it to fulfill a requirement. Our communities are getting some verbiage in their general plans, but yeah, they're not really too excited yet to really buy into the whole sea level rise problem. A collaboration of the Ocean Protection Council, the Caltrans, EPA, the Metropolitan, they all came together, California Energy Commission, and in March 2009 there was a report that was written by the Pacific Institute, and it's a really interesting report to read. It was kind of the first, I think, comprehensive state document that really did address this. This is online, but you know, you live right here, and it's very clear that 110,000 right off the bat people will be subjected to sea level rise, all of our coastal communities here. And you know, it's really interesting, this whole area. One thing that I've learned in dealing with these communities is that 25% of our coastal population in the US lives in Southern California. So that shows the density of our coastline, and we are very vulnerable here. This document online here, I just captured a few of the statements because I think that these words are beginning to show up now in our coastal community general plans. Flooding and erosion already pose a threat to communities along the California coast, and the increase in the future. And where the coast erodes easily, sea level rise will likely accelerate shoreline recession due to erosion. So they all make sense. Recommended that climate change must be integrated into the design of coastal structures. So this is an enormous statement, because now all of a sudden all of those coastal engineers, the coastal planners, the coastal commission, anybody permitting, all of a sudden has to face up to the fact and start dealing with sea level rise. The Coastal Commission has started to take this quite seriously. Their planning and permitting process now is addressing sea level rise. There's several meetings that have occurred. If you look at their documentation, there's an awful lot online as far as where you can go to and what they really are doing to include the process. These permits, I just pulled this one. Where is it? I think this is up at Ventura, actually, area. And these structures that are by the beach here, you know, it's the coastal, if they want to make repairs on this structure, what is the Coastal Commission going to do? Are they going to start limiting some of these structures right along the coastline? I circled this one here because I was going to talk a little bit about the run-up, wave run-up, and I didn't know if you really knew what that concept was, but it does occur when I looked at a lot of the permitting, a lot of the planning documents, you keep hearing this wave run-up. So I just wanted to point it out here, and I'll address it again in a little bit. So Dan has already given you a whole kind of background of the episodic nature of our ocean, of our sea level rise. This is a really busy slide, but I like it because it shows the complexities of what we're dealing with right now. And this is California today. This is it in 2100. So this is today, this is 2100. This is where our sea level, that red line, is where we are today. We have all of these oscillations going on. These are our El Niños, La Niña, and the Pacific Datal Oscillation. Those are natural oscillations that are going to be occurring. But then we have the tide on top of that. We've already seen pictures that Dan showed during extreme tides. That's when the most damage occurs. Then you put a storm on top of that again. And here's where the run-up comes into it. The run-up is after that wave breaks, comes ashore, how much of the water is actually going to run up past that. There's all sorts of algorithms to figure that out. Some say 1/4 of the wave height is going to run up, but really it depends. Is it a porous beach there, a structure? You know, is it a brick wall? Is it a sandy area? Are they cobbles? Is it a cliff? There's all sorts of variables that one has to look up to really figure out this run-up issue. And then we have up here is the inundation. So you can see this inundation is really variable. But the point is, it's going to start rising. You know, our storms getting bigger and more frequent. That's one theory that's going on right now with our climate change. So these storms of 1983 and 98 that Dan just pointed out, are we going to start seeing them closer together and bigger? That run-up is going to get more. Our waves are going to get higher. And of course, we don't really know what this ice loss is, and Dan did touch on that. This is actually in it was the 98 storm that was the second highest on yours, Dan. So this was not 83, because that would have even been higher. But this was in 1998 at Stinson Beach. The owner of this house is a friend of a coworker, and they actually finally did evacuate that house. And when they came back the next day, their grand piano had migrated to the center of the room, just from the vibration of the waves. But everything was intact. No windows were broken. So, you know, we know that storms are already affecting homes like this and have been for a while. And you just think about adding another meter on top of that, another 3 or 4 feet on top of that. What is going to happen to these homes? So there's a couple programs. Jerry mentioned I'm involved with both of these. One is CDIP and one is SCOOS. I know it's an awful acronyms. And these are federal and state programs, both through the Army Corps and California Department of Boating and Waterways and NOAA are all involved in efforts to really address and try to get a handle, and USGS. There are actually many agencies. It's just so happened that these are the ones that I'm involved with. So through CDIP, we do have this suite of offshore buoys. And what the Army Corps wanted to do, they started this program in 1975, and one of their missions was to get long-term waves. They wanted the 50-year wave study for the state of California. That's because they're responsible for structures along the shoreline. So they want to know for design thresholds, what do they have to design that jetty for, that breakwater for, armoring, et cetera. So we've seen, this is the 83 storm that Dan pointed out, Ocean Beach, southern, in San Diego, massive damage along the sidewalks there. And this program, by the way, is real time. These data are all accessible to the public. You have a really complex area here with the islands offshore. You know, in Long Beach area that it really depends on that wave direction, because Catalina is going to block it. Often it's really big waves offshore, but if it's coming from the west here or from southwest, you know, it might be blocked. So it really is dependent on that wave direction, and that's why the Corps and the Cal Boating have invested in this program to monitor this, not only for boating safety, but for long-term trends. Another project that the Army Corps is funding, and along with Cal Boating, is this process study for beaches in Southern California. And I think that this particular project ties in really well to the whole sea level rise issue. I don't know if you've ever heard of LIDAR. It's a plane that flies along usually about 3,500 feet. And it has light pulses. It's a remote light sensing instrumentation on board. And usually the swath is about 2/3 the width of the altitude. So like for 600 meters swath there, a light pulse comes down 35,000 light pulses per second is the instrument that we use. And it just measures very accurately within inches, centimeters, accuracy of the elevation of the sand or of the ground that it's being measured. There are LiDAR instruments that also measure the shallower area of the water, but we only use the topographic, the landside ones. So since 2001, the Army Corps has actually funded these LiDAR flights from the Mexican border to Long Beach. We have 15 flights that we've already collected. All of the data are accessible. You can grab those, download, look at that data yourself. And these are also our in situ surveys. So this is a little GPS sensor here, and that's a sonar that measures the depth. So why do we look at these observations? Because we're trying to get a handle on what is happening to our shoreline. We need to know this for inundation, flooding, but we also need to know this for sea level rise, because the amount that sea level rise is going to affect us is going to depend on how much our shoreline erodes or accretes. Right, so once again, it's the complexities of the tides, the wave height, the elevation, the run-up, and the sea level rise. Okay, this is an image of what that LiDAR will give you. And I just think, I mean, it's just really a cool technology that has evolved now over the past few years. The real estate agents, by the way, hate LiDAR because it shows them where you shouldn't buy a house. And this is, I had a direct contact with this in San Diego. Mission Bay is a very low-lying area if you've been there. And really, the real estate agent asked us to pull the image off the website because they did not want that in there. And I have actually a couple of the images I'll show you. But this is Alameda Bay, Seal Bay. This is your area in this neck of the woods. And this dark red here is 5-meter elevation. Now these are berms that we're seeing here, or very natural berms. They could be put there by a bulldozer. It wasn't necessarily from the waves coming in. All this shows you is the elevation. But it is very cool because it picks out immediately where the low-lying areas are. And this is a difference map. So then this starts telling you a little bit about, okay, in September 2004, what is the difference between February 2010 now in that elevation of the shoreline? And this is where it starts getting really interesting. Now you have to take out the lifeguard towers, you have to take out the restrooms on the beach, whatever. So you have to know a little bit about how to look at the data, but there's an awful lot of information in there. And LiDAR is really one technique that within the state of California now is getting some traction because everyone is realizing how valuable that is in tracking our shoreline, and I think, Dan, in tracking the ice pack in the Sierras, right?
We're hoping to measure snow.
Snow, okay, that's it. So, all right, so this is the these are the LiDAR flights that I told you that we have flown since 2001. So for the California Energy Commission in the 2050 report, and this was in collaboration with Dan, we took some low-lying areas, and we did produce these sea level maps. So this is the one over here that goes out to 2050, and these projections with Dan, we came up on what we projected out the waves, we added projected sea level rise in here, and this is actually down by Imperial Beach in the Tijuana estuary. Wetlands, of course, are very vulnerable, and they're very precious to our society, so we're all worried about those. This one projects it out to 2100. The thing is that you can see already how much of this is vulnerable, and this does not include the erosion that is going on during that time period. So that's really a big factor in this. That's why the Corps is trying to get a handle on what the erosion on the shoreline is, because it's going to make a big difference if you have lost 10 foot of your beach and you're getting the storm of the century, and then you have a high tide, and then you have another foot of sea level rise on top of that. That all starts adding up. And that, I think, is where the complexities of this whole issue come into it. The sea level rise is one component we need to look at, but we need some really good observations to give us these baselines. This I just love because this was in the January 2001 storm, and this was in Mission Bay in San Diego, and already, you know, they're having to deal with the flooding during the streets, and I keep thinking, wow, if that was a meter higher, you know, what would happen then? So one of the projects that through the SCOOS, this wonderful acronym, had funded last year was actually to look at the inundation in Cardiff. Sorry so many of these are down in San Diego area, but that happens to be our study area here. So this is an area, if you've ever, Encinitas along Highway 101, there's a very low-lying area just south of Encinitas, between Encinitas and Solana Beach. And this is the Chart House parking lot there. During high storms, that whole parking lot can be flooded. This area right in here is, so this is Highway 101 coming down, Highway 1, and there are portions of that where the pavement is actually completely eroded back, and the cities have cones out, very vulnerable to wave action. It's right on the beach there. So the red dots are actually pressure sensors that were buried this last winter. And the reason why they were buried there, because we're trying to get a handle on this run-up, because everybody, we know the wave height, right? We actually have a buoy right offshore here, a wave buoy. We know that wave climate hitting the shoreline. We know the topography, the height of the beach there, because we have our LiDAR surveys. But when that wave breaks, we really don't know how far up that whole run-up, all of that swash stuff will come on up, and how much of that is actually going to start overtopping Highway 1. So we buried pressure sensors along there, and we also put up video cameras. And let's see, I think that what we are working with the city of Encinitas, and we are now sending them automated messages 3 days out when our records indicate that that area of the Highway 1 is going to be overtopped. That's because their planners, their engineers, their lifeguards have to go down, cone it off, they divert the traffic. And so we have these waves, we have these tides. There's not a run-up factor that's included in this particular plot, but we're looking at it behind the scenes, and the run-up can be significant enough that it is a factor in this whole thing. So this is, I just want to emphasize that the communities like the city of Encinitas are dying to have this type of information, because this really helps them for their planning and their logistics, and also in their design of the community going forward.
Well, it's just on the real estate people.
That's right. We just can't deal with the real estate agents, yes. So this is just such a great shot. This was on Thanksgiving Day 2001. We had just had a beach nourishment at Torrey Pines. 6 months earlier, waves came. Look at what happened. I mean, all that sand just went out, and we were left with a highly eroded beach there.
Did it come back that next summer?
It didn't come back to that height. It did come back a little bit, but it never got completely back. You know, we have a lot of armoring on the cliffs in San Diego. We have a lot of structures that don't have armoring yet, that their porches are literally falling off. The Coastal Commission is not re-permitting some of these homes there, because we know that those cliffs are very vulnerable. They're getting eroded away at the bottom, and that's with our storms and our tides right now. And we just think, you know, as sea level rise goes forward, we need to just really start taking that into account. We need to continue mapping and monitoring, so we get these baseline measurements so we know what's happening. We need to come up with these comprehensive floodplain management plans. We need to identify the land risks. And then we need to decide what to do about it. You know, do we continue to fortify that structure, or do we cut it in half and take the coastal cliff part away? Or do we just relocate and say, okay, that one's going to be written off, build back 500 feet or something, and go on to the next thing?
They charge the people for removing it, they'll build the next one further back.
That's right, that's right. Okay. Am I going here? Here? Is it stuck? Ah, there we go. All right. I put this in here again just because I wanted to let you know that in the state of California, I think people are really beginning to state, at the governance level, sea level rise is becoming a buzzword. I mean, I can tell there's more and more meetings about it. The Coastal Conservancy Ocean Protection Council funded a LiDAR flight from the Mexican border to Oregon, the whole coast of California last year, up to the 20, back to the 20-meter contour. So that means from the water edge all the way up until the elevation is 20 meters, so 60 foot plus, right? They have that whole area mapped now, and that's because they wanted that baseline survey. So that's great. We got our wetlands, we have harbors here at Long Beach, Port of LA. Those are crucial harbors to our economy. You know, they're very vulnerable to sea level rise. Whoops. Go back one. Up. Okay. Oh, darn. Jumping around. Can you find it? I just think I have a couple more here. There you go. Right, there's a survey now out that Dan and I have both participated in that is sponsored. I think USC Sea Grant Office was really the lead agency here. But there's many agencies that are involved, and there's others that aren't even up here, which are very interested in, this is a survey that is going out to the community managers, to coastal managers, and trying to find out where are they at with the sea level rise planning, and how much have they started to integrate plans into their city documents. Because, you know, it's like a lot of people do know, and it's becoming the buzzword, but it's still really a difficult thing to deal with, you know. And the LA Times does have these articles now. This was just on March 2011. A couple months ago, you know, how are we going to build these resilient communities? And in summary, I just wanted to say that we are seeing sea level rise being addressed. I think at the local area, it's probably the slowest getting integrated, is what I've seen. At the federal agency, they're mandated through legislation now to take it into account. At the state level, there's a lot of awareness. When I've actually talked to planners and engineers at the city level, it's like, yeah, they have the verbiage in their planning documents because they're supposed to, but they aren't too, you know, sure they want to jump on the bandwagon and really start considering sea level when they're issuing city permits for building. And once again, the sea level is just one of the components there that we really need to look at. Yeah?
Well, at the federal, state levels, you can take a 30,000-foot view and just put
That's right.
documentation of what should be. At the local level, you've got
Very difficult.
You've got to engineer it,
I know.
which means you need data. And this looks like brand new data, so maybe they haven't had enough data to work with.
Well, there's definitely not enough data. We're data starved here. And that's the reason why I wanted to show you a couple of the efforts that are going on. And truthfully, in Southern California, we have more LiDAR data than any other community now in the US. And we're very fortunate that we have the Army Corps participation in funding that. But I mean, isn't that your experience, Jerry and Dan, that we're pretty data starved? These baseline elevations, these baseline waves, even the waves. CDIP has been in existence since 1975. We have wave gauges that go back and started continuous records from 75. But the problem is the technology, and so people look at our records and they go, oh my gosh, yes, bigger waves, you know, more frequent. Look at the CDIP buoys are showing this, they're all over. And then I have to remind them that the technology has changed. In 1975, we transmitted that data from the wave buoy, an HF antenna, back to a shore station on the shore Whenever there was power outage, whenever there was phone line outage, because we were sending the data across a modem at that time, that station went down. Now our buoys have Iridium satellite transmissions. They go up to a satellite, they bounce to the DoD gateway in Honolulu, come back to Scripps, we process it, send it out to the National Weather Service. It takes about 2 minutes. So yeah, we're getting a lot more bigger waves now. We're capturing a lot more waves, but that's because we're not, dependent upon the power and the network or the communications. So I think you need to, it's very difficult when you try to get these baseline observations and then say that this is the trend that's happening. Yeah.
How do you get your LiDAR survey information as a layperson?
You know what? It's on that website. Jerry, maybe you could.
We'll make sure people get
Okay. There's a website at NOAA. It's called Coastal Services Center. Jerry works very closely with them, and they have a wonderful site. It's called Digital Coast. You should check it out. They have inundation models on there. The LiDAR is free of charge. All of this data that I showed you, the wave data and the LiDAR, are completely free of charge. Also on the CDIP site, which I'll send you, you can get those images that I showed you, the difference maps. If you just want the image and not the data itself, then we have some on our CDIP site that will give you LiDAR from the Mexican border to Long Beach. If you want the actual data, then you need to grab it from NOAA, because they are really large files, and it's a great distribution site.
There's actually a website you can type in your address and it will come up with a map. I put yours in while your house is in trouble, but you should donate it to the aquarium. Write it off as a gift.
See, that's why real estate people don't like these things.
But there actually is a website.
Yeah, there is.
It's kind of
It's a great site. Wait, there was one right behind you first. Yeah.
So you say your stars for data, what specifically kind of data that in your country world you would have? What data streams?
What would we have? Well, just that we know, the tidal data we have a pretty good grasp on. So that I would say is good. The wave data, we're trying to get this baseline, this long-term history. Run up, we don't know too much about, we're learning. And then there's all of the data that Dan deals with, which is all of the atmospheric data. And oh my gosh, there's a whole suite of it there, right?
I want to come up front because, scientists love data. Data are of absolutely no value to a decision maker. They want information. So now clearly you're creating informational products. But we're going to have a panel during Capitol Hill Ocean Week in Washington in about 2 weeks. And the panel is, will increased ocean knowledge improve or increase national security? And I have the dubious distinction of chairing that. all of you guys want to say, invest more in research, it'll contribute to national security. But it only will, I think, if you can pull the switch to translate the data into information, to tools.
Right.
And what you were saying, the land use decisions are all made at the local level, except for state parks and federal reserves and military bases. But that's where the rubber hits the road, when you're the city manager, the city council, the mayor, because that's where land use decisions are made.
Right. Well, another thing that strikes me, Julie showed cliffs that are eroding Encinitas' example. Do we have records of cliff retreat that are?
We do. So Adam Young, actually we have one researcher at Scripps now. He works for Ron Flick. He's dedicating their lives, their study to measure that retreat on cliffs, because that is a big thing. But it's not since before 2001 at the most.
I think a very compelling piece of evidence is because these processes happen so episodically, that we need to be able to demonstrate that there have been large erosion episodes historically, and sort of the run-of-the-mill winter, maybe nothing happens.
Right.
Not that much. Geology doesn't happen uniformly, as you all know. It happens in spurts, and I think that's up to us to be able to demonstrate. And part of the challenge with this observational problem is that during these big storm episodes, when everything is happening, it's the most challenging time
Oh, definitely.
to collect data.
You can't fly LiDAR during a storm, by the way. You have to have perfect visibility to the ground, no clouds. It will not penetrate a cloud. That light beam coming down has to be no interruptions between the plane and the ground. It's also a little bit difficult to get permission from LAX once in a while to go by, and a few minor details, logistics, yeah. But right, and Jerry, it is taking this data and turning it into useful products, and that's really what SCOOS is all about. They're trying to get these products out to the decision maker in a form that they want and customize it to each user. Yeah.
This is a presentation technique for your, out in DC, and it's also the people who are going to take data about a coastline and waves and turn it into information about decision making sounds a hell of a lot like the military to me. You know, they've got to be good at this. I mean, they've got the CB beach down there, the LCAC landing craft.
Well, we work with the military a lot, actually. At Point
Designed to
Magoo.
turn
Yeah.
80% of the world's coastline into accessible landing area. They've got to have models about this, and there's your lead into national security.
Because that's interesting, because within academia, you get promoted and tenured and honored by publishing papers in the peer-reviewed literature, so you're contributing to the knowledge. But moving into the public policy arena, it's a nasty
It
arena.
is. It's very nasty. It's not just the real estate agents. It's all those other people. Yeah.
It's Bob, and then in the back, and then what?
But you know, I think this is a great comment. I think you know, one thing that is emerging in this arena, it's not exactly the answer that I think Jerry was after, but more and more, I think we are trying to look at scenarios, and I think that's one. You know, in military planning, I think they do scenarioize, and you know, they look at what if sort of situational kinds of things, and I think we have to do more with that. And as you do that, I think that, you know, this notion that it's bringing in, you know, more and more forms of expertise, and it doesn't end at, you know, it doesn't end at us, because we are more, I guess, leaning towards the academic side, but really you need politicians, and you need, you know, you need people that are working in the community, you need planners and so forth. So it takes you know, it really takes, you know, an army to actually pull this off. So we're just part of the
Expertise, decision theory, and so on, right?
Right.
Yes.
Yeah, it's kind of a sidebar, showing practical values and such. We have a friend who's a geologist at a high level and writes textbooks and teaches at Caltech and so on and so forth. And he has a work study he has his students do of the greater LA area, the areas that are most unstable, cliffs, avial fans on the mountains and
Right.
stuff. When you overlay it with a real estate map, that's the most expensive property. Isn't that
Right.
interesting?
Yeah.
We all should build in Westminster,
Yes.
not in Naples. But what's the most expensive property?
And often, we in California, we think we should get rid of flood insurance for those crazy people who build along the Mississippi or so on. But we build in earthquake-prone areas, mudslide areas, fire-prone areas, so it's all,
Yeah, it's all-
with your own perspective. Yes?
So a lot of the focus with this is on community development, but is anybody modeling how the inundation, especially of wetlands and salinity lines moving up rivers, going to affect population dynamics of fisheries? I mean, you're losing rearing grounds, you're moving salmon habitat, which then will have economic effects on, you know, fisheries.
That's a good point, because, you know, if you look at that chart you put up there, wetlands have been around for tens of millions of years. They've seen sea level go up and sea level go down, they move. What's different now? They have no place to go.
They have no place to go,
They have no place to
and they're just being encroached. They will be encroached upon.
That's right.
And then particularly with the development behind them, I mean, most of our wetlands areas are surrounded by homes now, a lot in Southern California.
And fill up into forests, fields,
They
and
have no place to go. Now,
The
so
swimming pool, they built a swimming pool.
if you're the mayor of one of these communities, you could go to the city council and say, guys, I want us to sacrifice half of our city, we're gonna make a corridor so the wetlands can migrate. Yeah, probably wouldn't get you very popular. But it is a real, it's a real issue.
I mean, especially because, I mean, well, when Salmon closed, I mean, that was a huge economic impact on California, especially, in Oregon too, but,
Right.
I mean, there was like federal relief that had to come in for it.
I want to come back to California a second. One of you had to that. As I recall in that report, Marin and Orange counties on the open coast are far and away the most, they will have the most
Vulnerable.
damage. If you include the total coastline, San Francisco Bay
Right.
is much more vulnerable. Orange County, though, the loss of property value, it's hundreds of millions of dollars. I've forgotten what it
Yeah.
is, but it's huge.
Yeah.
There's another footnote that was sort of underscored by the Japanese earthquake. And, you know, we live along a geologically active area in the West Coast, particularly this Cascadia area
Subduction.
that is Northern California up. And it turns out that there's been this fascinating work that has uncovered these buried forests that have occurred periodically, actually not really periodic, but on the scale of 200 to 600 years, there will be an event. It's a big event that's caused by the plate slipping and the continent reacts. So there's also this issue of sea level rise that happens in 10 seconds that we haven't talked about, but you know it's definitely an issue in Japan now that coastline. You know, there are communities that are just totally submerged, and a similar thing happened in Chile and then in Indonesia. This in the last few decades. So these are things that globally, you know, there are these forces that we often ignore, but could be really, really significant.
We're really just full of good information tonight.
Yeah. Next week, we'll talk about some of the local and regional changes. Globally, you can either change sea level by increasing the volume of water, by heating it up, or by adding new water, or you can change the size of the bucket. And that's happened over geologic time also. But locally and regionally, you can print the edges. You can either make them go down, like the Gulf of Mexico, so apparent sea level rise is much greater than global, or you can move it up like we do in Alaska, and apparent sea level rise is much lower. In fact, in parts of Alaska, the land is rising more rapidly than the sea, so if you're looking out of your front window, it looks like sea level is actually falling. So it's a curious, there are a lot of interesting aspects to this game. Bob, just a second. I want to, with not much happening in the last couple of decades along our coast, but as you mentioned, that could all change. And in fact, sea level might rise more rapidly along this coast than the global average, so that we would catch up, which will then compound all of the things you've talked about.
Yeah, because the Pacific wind system shifts.
So Roy, I really think you ought to donate the house.
Yes, all I wanted to mention was it is very important for the cities to know. We know the cities financially can't handle it. We know the counties can't handle it. We know the states. It's going to be the individuals. But if you don't get the data to them, they can't get together to do it themselves because they can't afford it. You call them and say it's going to happen tomorrow. They can't get there. But over time, they could get there. They could build walls. They could build recommendations that you would have for this, but they need that data.
Well, I'm glad you said that, because that's our feeling completely. He's great, Jay. You're going to hire this guy.
They need the information derived from
I
that
know,
data.
I know,
You wouldn't
I
know what
know.
to do with that data.
No, I
But I know what he means. You need that data collection to get the products out there, you know? Yes.
Bob is next. But Bob, he operates the San Jose nuclear power plant. He's the
Oh.
Southern California Edison.
Bob, I think I know him. Dick Seymour, right? At your house? Yeah. We have met. We've sat and had coffee before.
So, speaking of data and city planners possibly being confused, I thought I heard Dan, I kind of listened, what you're going to give a general sea level rise for 100 years. I heard 1.5 to 2 meters,
At the upper end.
and then Julie's slide showed 3 meters.
Julie was talking about the run-up on top of the.
So that,
sort of
yeah, so you
still
said you're going to get
ocean
back
level.
to extreme run-up, so that includes.
That was
looked like-
including the extreme
but it
run up
looked like-
here.
But you said the red line was just.
The sea level rise. And you know what? That wasn't really based, that was to show you an example of the complexity of it. You should go with Dan's numbers.
But again, I
That,
Isn't it, there's range?
there is a range, there is a range. And with the ice melt, I think that's on the right-hand side, we said the ice melt, I mean, if there's massive ice melt, it could be 3 meters.
Yeah, you got a greater too.
yes.
Well, okay, so just a little historical note that the estimates of global sea level rise, if you would have polled scientists 10 years ago, you probably would not have gotten these
Well,
the
you know,
numbers of this magnitude.
I was sitting in a meeting in San Diego where Walter Monk packed out a room. And I can't remember if it was 10 years ago or 20 years ago.
Yeah, he was.
Yeah,
I'm sure he was less.
He was talking about 10 centimeters.
Yeah.
Yeah,
But
I
Walter,
just-
I think, would concede that. See that.
Things are changing.
Things
Well,
are
we know
changing.
from the record, we know from the altimeter record, these satellite observations since the 90s now that there is an acceleration of sea level rise globally. That, it went from about 2 over the 60 years before that to about 3, we think, in the last 15 years. And we know that the rates of melting in both Greenland and also Antarctica, West Antarctica, have increased over a relatively short period. So we're seeing these symptoms of warming, and anyway, the evidence is kind of accumulating. Getting to the upper end, though, there have been some studies about the physical constraints of sea level rise, because where ice can flow out of these the big ground-based sources, which are Greenland and Antarctica, and it's thought that about the upper end of global average sea level rise by 2100 could be about 2 meters. The lower end of what estimates are right now is something like 2 feet, between 1.5. But when you compare that with 7 inches over the last 100 years, so we're seeing something that ranges from 3 times historical rates to 8 times historical rates. It's a lot. It's a big, big problem. And when you think of the geopolitics of not only Laguna Beach and the Bay Delta, but when you consider all these low-lying areas, not only in the United States, but this is going to displace a lot of populations. So I think our military is really, really concerned about sea level rise.
Yeah, actually, I just have to say that 3-day warning, that automated message that goes to the city of Encinitas, we also send that to the weather station at Point Mugu Navy, because they have a place that overtops also, and they have to evacuate right there during that time period. So they've given us a threshold, because with LIDAR, we know that berm elevation, right? And during a south swell, there's that one beach, and it overtops, and they have to get their people out of there. So it does have impact for a lot of different type of communities.
Who else has it? Larry?
Turning it into information and decisions
There we go.
involves education, and the people on the front lines that a lot of people listen to because they don't even have an axe to grind would be architects and civil engineers. How many schools have programs about dealing with coastal sea level change and tsunami effects and things like that? You'd think maybe somebody would be doing that, but I've never heard of any. But
He's an engineer.
Well, I think a lot of this, this is an emerging
It's new,
science.
yeah.
And there certainly are coastal engineers, and there's a very active coastal engineering community, and Julie is closer to that than I am. I'm actually pretty impressed at the breadth of expertise, even if it is still somewhat academically centered. I think the penetration into the outside community, as Julie was pointing out with this survey, it reveals that there's quite a difference in the level of understanding and the capacity and so forth. But my impression is that the education and the level of knowledge across the board on these environmental issues, including climate, is rising very rapidly. That's a good thing. It's another story in terms of translating that into policy and implementing it. I mean, that's very, very difficult, and it's complicated by politics, as you all know. I mean, but education lies sort of at the heart of it.
Yeah, it was very telling in one of the cities that I actually talked to, based on the survey. They didn't take the complete survey, but I kind of had the survey questions. And before coming up here, I wanted to see, well, how much, are they really integrating these thoughts about sea level rise? So I knew somebody in the planning department already, and I went to them and they said, oh yeah, we're getting it into our general plans. We now have all the verbiage there. And then she goes, but let's go over and talk to the engineering department. And we walked over there, and he goes, oh yeah, it's in the verbiage, it's in the general plan, but no, we're not really enforcing anything yet, and we're not really integrating, changing our plans for coastline development or whatever. So I think that it's starting to penetrate in the cities, but you're right, it's a big education process to really see how we can implement some of these things.
The other thing, if you would have taken a poll in New Orleans before and after Katrina and asked them how seriously they considered, storm surge and all that, I'm pretty sure you would have gotten a very different result. And I think once we're sort of, we can visualize these issues, and sometimes it takes a disaster. And I can enumerate other cases. Drought planning in the United States was non-existent before the 1930s when we had a Dust Bowl. But once that happened, all sorts of things that developed. And I think that we often learn the hard way, but we do learn.
We probably need a disaster in San Francisco. Big level.
Well, you're having Will come to talk, right?
Because, there's a case, it's more vulnerable than New Orleans was before Katrina.
We've only very recently had large populations that were affected.
That's true.
Yeah,
Triple in my lifetime.
most of that area is below sea level. Thousands of miles of dirt levees. The Army Corps of Engineers has said they are less stable than the levees in New Orleans before Katrina.
That's right.
And we still have not come to grips with that. So that 50% of our water supply in Southern California, and we don't have any alternative right now that would replace that. Yes?
I know Linda had a little knowledge about LEED certification, but I believe that this building, LEED certified, in conjunction, I believe, with the government, EPA and so forth, is on that level at least. I don't know, one, how much it's really taking off the ground, it's a newer program, and two, and within that, are they including courses and knowledge on the concept of climate change? I'm just curious if anybody knows.
Leadership in energy and environmental design, environmental and energy design. This is the LEED Platinum, which is the highest rated, but sea level does not.
I'm just curious, I mean, within that concept, if this is an area to put it in.
I think that the city of Santa Cruz in California, from what I've heard, is the only city that I know of where the permit process actually does take into account sea level rise in some of the areas here. I've heard that that's our first community to start to actually implement that.
And there are only a couple in the United States. There's one in Florida, on the west coast of Florida, and they actually now, it's a policy that they have begun systematically to move upslope. And so if your house gets damaged by any kind of storm, you can't rebuild there, but the city will give you a piece of property and
Interesting.
that, just what, Corinne, John and then Corinne.
On the city of Oceanside, I know if you are building homes near an estuary, they're making you build it up at least 3 feet, maybe even 5 feet
Oh, okay,
higher.
interesting to know. On the wetlands area
Yeah,
then?
so you have to raise it up above. So you basically have this layer area underneath the house. And also, city of Oceanside, back in about 68, right around there, I can't remember exactly what year. Basically, all the homeowners along the whole city put in rocks in front of their homes.
Right.
To prevent
The revetment.
disappearing.
Yeah.
On Galveston Island, you have to have your houses built up on stilts, and you have to have them oriented so that if there's a terrible storm, it'll come in the front door, go out the back door.
Ah, see, that's what that
And,
cartoon
By
was.
changing the orientation of homes and streets, you can reduce a lot of the
That's what this guy did. Oh, next one.
Well, two things. As far as cities are concerned,
Still.
I think it was yesterday that Hermosa Beach
Mhm.
had a symposium or a workshop that was totally dedicated to climate change and how it was going to affect
Great.
Hermosa Beach.
Mhm.
That's one thing. In the education process or in the motivation of city planners, I think we need to look at the Mark Mead thing and get citizens on the advisory committees and to motivate the city planners. I'm going to use Seal Beach, which is on your map as an example.
Right.
The draft coastal plan, Seal Beach is still not submitted to the coastal plan. Whoever wrote it, which I assume was the city engineer and the city planner, said that sea level rise in Seal Beach was not really a problem in the first place.
Interesting.
It was the.
Okay.
I don't know.
Just don't show them the LiDAR flights, okay?
He's a little over 60 years
I was gonna say, why did they build those things for?
Sea level rise is not a problem. But a group of citizens got on the advisory committee, and they're changing all that. They're really the motivators that are educating the city planners. So somehow you have to get
To tie it all in with the
ordinary
people.
people in every city who are gonna drive the city politicians.
No, that's a good point. So 2 weeks from tonight, you'll hear the chairman of civil engineering from UC Irvine. He's going to give that perspective. And he's going to share the evening with an artist from the Art Center College of Design, who was in charge of the project they did for us on sea level rise. And then 3 weeks, you will be hearing Will Travis. Will Travis is the executive director of the DCDC, the Bay Conservation and Development Commission. He's been the head of it since it was formed, and it was formed, I forgot, 30-some years ago, and it was formed because it was concerned by people living around San Francisco Bay that the bay was getting smaller because people kept filling in to extend building out on the bay. And now the irony is it's getting too big, and these same people are worried that the bay is going to go through their houses. So you'll hear a very interesting perspective from Will Travis. And next week, you're stuck with me.
Maybe I'll come back to that one and learn something, huh?
I'm going to talk about some of the global issues, but you've had the benefit of two outstanding scientists this evening. I can't.
Thank you.
Thank you.
I have to tell you, see, I was an oceanographer. If you're an oceanographer, you either have to have a beard or you mess your but I never grew a beard. And I think one of the most memorable evenings in my entire life was when I was a graduate student at Harvard, and my wife and I went to hear Carl Sandburg and Robert Frost. They were on the same stage together. And if you two literary giants, and if you've ever seen pictures of Sandburg, his hair was always slicked down, kind of like this. And Robert Frost was more like Dan. my friend Robert Frost is in the back. He has to mess up this area. Thank you.